In this video, we will talk about OR gate logic, and we will have this circuit you can see in the figure, and we will try to prove that the network presented in this circuit belongs to OR logic. So we have to prove that, and there are some steps to do that. So it's really easy. First thing which we should recall is that for diodes, we must know that a diode is in a forward bias condition if its positive terminal is connected with the positive terminal of the battery. Okay, so this is forward bias condition. And if a diode's positive terminal is connected with the negative terminal of the battery, then this is reverse bias condition. Okay, you must understand these two concepts before trying to solve the problem and try to prove that this circuit belongs to logic OR gate. Why? Because we have these inputs over here, and these inputs are fed to the network, and then we have to see if it is connected in forward bias condition or reverse bias condition. So let's see how we are going to solve this in next slide. Now the circuit given to us is a two-input circuit. Let me redraw it over here. We have an input which is V1, and then we have second input which is V2, and they are connected with two different diodes. This we have D2, and then they have this common node, and it is connected to a resistor, okay, which is grounded. So we have V1, we have V2, we have D1, we have D2. So the first condition is that we have to see what happens when we have an input at V1. Let's say we have 5 volts, and we have no input at the second terminal over here, right? So when we apply the battery source to this input V1, we can have two conditions. One will be to see if the diode is in forward bias condition, and the second will be if to see we have to see that the diode is in reverse bias condition. But it's obvious to us from this figure that the diode is in forward bias condition if the battery source is connected in a way that we have positive terminal connected with the positive terminal. If in case we have a negative terminal connected with the positive terminal, so we will have this situation. We will have a circuit over here like this, right? Negative terminal, positive terminal, and here we have this diode, right? So we can see here that the negative terminal is connected with the positive terminal of the diode, so there will be no flow of current. So when there will be no flow of current, then it means we will have an open circuit over here, right? And for the second input, we already assume that there is no voltage applied to it because we are talking about case number 1. So if there is no voltage, of course, there will be no flow of current, and we will have an output of 0 volts. What happens when we have a forward bias condition? When this terminal is connected with the positive terminal of the battery. So in that situation, our diode will be in the forward bias. We will have a diode over here. If you recall the figure from the previous slide, it will be in the forward bias because positive terminal will be connected with the positive terminal. So in that situation, what happens is that there will be a voltage drop across the diode. And we know that the voltage drop across diode is 0.7 volts. Okay, we know this. And this is for the diode made up using silicon material. Okay, so now we have this case number 1, input at first terminal and no voltage input at the second terminal. For the second terminal, it will of course act as an open circuit because no voltage is applied. And for the first terminal, now we can apply KVL, which is Kirchhoff's voltage law, and see what we get at the output. We already see the result over here, so let's verify that. So let's apply Kirchhoff's voltage law over here. So we will have a Kirchhoff's voltage law, and we see that the input voltage is minus 5 volt, right? from here. Minus is the first terminal, so I use this approach. If you are using the second approach, then this will be plus 5 volt, and then you will have to use the second terminals of these components. So let's use the first terminal. So minus 5 volts plus 0.7 volts plus V naught equal to 0. This is the Kirchhoff's voltage law, because current will flow through this and it will act as a linear, or you can say a circuit in series. Okay, so let's skip these V's from here, and this will become minus 4.3, right? Plus V naught equal to 0, and we will have V naught equal to 4.3 volts. Okay, so for the first condition, we have an input of 5 volts at first terminal, 0 volts at second terminal. We got 4.3 volts. Clearly see, when we have a one input to the circuit, we are obtaining a result at the output, which is 4.3 volts. Okay, now let's go and solve the second case, in which we will assume there is no input at the first terminal and we have some input at the second terminal. In the second case, just like we discussed previously, now we have an input at the second terminal. You can see over here, we have an input at the second terminal. This diagram actually belongs to the previous case, so don't get confused with this diagram. So we have an input at the second terminal. We will have input over here, right? Positive, negative, and we will have no input at this terminal. So this will be 0 volts, this will be 5 volts. So we will have an open circuit over here, right? Just like the previous case, we don't have to get like a lot of confusion in this. Only what will change over here is that in this situation, this will be open circuit, and this will be a battery source of 0.7 volt. It's the same concept, but we now have an input at second terminal and no input at the first terminal. So once again, this will become a series circuit, or you can say like the components are connected in a series, right? So this becomes minus 5 volt. Apply Kirchhoff's voltage law, minus 5 volts plus the voltage drop across second diode, which is 0.7 volts, plus V naught equal to 0. V naught is actually voltage across this resistor. Okay, so this becomes minus 4.3 volts plus V dot equal to 0, and V naught is equal to 4.3 volts, right? So once again, we saw that in the second case, when we have no input in the first terminal and there is some voltage applied on the second terminal, we have this value 4.3 volts, and in logic gates we can assume it to be equal to 5 volts. Okay, so previously we calculated this as 4.3 volts. I assumed it as a 5 volts and wrote it here as a 5 volts, because for logic gate, 1 acts as an on state, 0 acts as a off state. So you can simply write these values directly over here. Now we will go to the third case, where we will apply voltage to both terminals and see what happens. In this case, we can see that we have an input voltage of 5 volts at both terminals. So we can say that there is this common voltage source, right? And it is 5 volts. And then it is grounded, or you can connect it over here as well. So now what happens is that we have an input voltage at both terminals. Once again, the first step is to see if the diode is in forward bias or reverse bias condition. But since the circuit is already obvious to us, it is constructed in a way like this. So we know that this will be in forward bias. Okay, so for diodes, we know that the voltage drop across a diode is 0.7 volts. So this is for the D1. For D2, once again, it is 0.7 volts. So this is for D2. Now the key point in this case is that this diode and this diode, they are actually in parallel. So let me draw it over here. This is 0.7 volts, right, for D1, and this is for D2. So if you look closely, they have common terminals. This terminal, like this node or terminal, they are common. So we can say they are parallel with each other. So when components are in parallel with each other, the voltage drop across them is equal. And we can already see it over here that they are 0.74 diodes. So the Kirchhoff voltage law actually becomes much more simple in this case. So how we are going to do that is that Kirchhoff voltage law will be same as before, minus 5 volt plus. Now the combined voltage drop across this parallel circuit. So that is 0.7 volts plus V naught, which is the output across this resistor equal to 0. So this becomes minus 4.3 volts plus V naught equal to 0. V naught equal to 4.3 volts, which is equal to, roughly equal to or approximately equal to 5 volts in terms of logic gates. So I can write 4.3 volts approximately equal to 5 volts. Okay. Now, the fourth case is to see if there is no input applied to the input terminals. Now, this becomes really easy because when there is no input applied to the input terminals, this is for the case number 3. Okay, don't get confused with this. This is for case 3. So when there is no input applied, this will be open circuit. This will be again open circuit. Okay, here, let me redraw it because this looks like a battery. So much better if I redraw it. Okay, so the thing is, this will be open circuit. This is D1, this is D2, common terminal, and grounded. Sorry, goes to the resistor and then grounded. We have to calculate output voltage over here. So if there is no input voltage over here, there will be no flow of current. And if there is no flow of current, there will be no output voltage measured over here. So in this case, it is really obvious and easy to understand that when there are no inputs, we have no output voltage. So we can directly write it as a 0 volts for the case number 4. Is that clear? So now what we are going to do is that we are going to verify this table, which we obtained for this circuit, and compare it with the OR logic gate. For OR logic gate, we know that when we have one input and second input, then the output result is always like on state. Let's talk about the states. State 1, state 2, and this is output. Okay, so when we have this kind of result, we call it as OR operation. Actually, in simple words, whenever we have only one on state, remember this. So result will always be on. Okay, this is for OR logic. So let's see in the next slide and compare OR logic gate table with the table we created for this circuit to see if we have proved this to be a OR logic gate circuit. So here on the left-hand side, you can see we have this OR logic gate circuit. We can see we have one input, which is, let's say, on state, and then we have off state, but the result is 1. So we can clearly see over here, we had 5 volts for the first terminal, 0 volts for the second terminal, and we calculated V output to be 4.3 volts, or let's say it is approximately equal to 5 volts. Similarly, for second case, we calculated 5 volts. For third case, we calculated 5 volts again. And for the last case, it was 0 volts. So if we compare this table on the left-hand side with the right-hand side, we can clearly see we have one, let's say on state, we have 5 volts, output is 1, we can see output is 5 volts. Similarly, for this case, it is same again for the third case, where both states are on and we are obtaining some output. So we saw this for the third case, that we had input voltage at both terminals and we calculated an output. And for the last case, when there was no input voltage, we saw the result is 0 in both cases. So we have proved that this circuit actually belongs to OR gate logic.